In this recording, I'm going to demonstrate the analysis of the ion exchange experiment that you performed in the lab with these syringes and the high trap Q columns. The data that was collected was based on the assay for PPO activity with the substrate dopamine. Dopamine is oxidized by PPO or polyphenol oxidase into aminochrome, which strongly absorbs at 480 nanometer. So all the data listed here for your starting material and the different fractions that you collected comes from the spot checks for PPO activity with dopamine as a substrate. Below, you see the same type of samples again, but this time the Bradford reagent was used to detect protein in general at a wavelength of 595 nanometer. To make the graphical presentation, we will click on Insert and then select a bar graph or column chart, maybe the 2D column right here on top. Then I'll go to Select Data, and I'll first add my data series with respect to the measurements taken at 480. The values are right below. Those are my series values. Instead of the numbers 1 to 14, I want the actual description, so I clicked on Edit, and I'm inserting the names of the samples. In addition to the data collected at 480 nanometer, we can also add all the data collected at 595 nanometer. And this is the data with the Bradford samples. The sample names are the same, so I can adjust them if I wanted to, but they would be taken by the other. So right now we have both signals displayed, one in blue and one in orange. Without the legend, we wouldn't know who was who. So here it would make sense to include a legend. Unfortunately, the way the colors were chosen is exactly opposite with how the colors appear in your plate. So this is why it is worth our time to switch the colors. You could, for example, start in reverse and first plot the data at 595 nanometer, and then you would get blue, and follow up with the data at 480 nanometer, and then you would get orange. Or you can click on one of the data bars or columns. You then get the opportunity to format your data series. So I'm going to click on the first icon, and I'm changing the fill by clicking on Solid Fill, and on purpose I'm going to select the color of a dark orange for everything collected at 480 nanometer. I don't want a line, just the graph as it is. Next, I'm going to click on the data collected at 595. Again, solid fill, this time dark blue or any blue color, and no border is necessary. Note that you also had the opportunity to separate the two data series. There is this symbol for secondary axes to optimize the y-axis range. So one goes from 0 to 1.4 and the other one from 0.27. But in this case, the series do overlap too much, and we would not be able to really separate them out even with a gap. So I'm not going to plot both of them on the same or on different axes. However, it might be worth considering adjusting a baseline, because the Bradford reagent itself absorbs light somewhat at 595 nanometer, and you can see that buffer A and buffer B, who should not contain any protein, it's just an aqueous solution with tris with and without salt, so no protein. We could, for example, subtract the absorption of all these values to get a cleaner graph. So right here, I can generate 595 minus baseline as a shorthand notation. And for each value, I'm going to subtract one of the values of the buffer. So this one, for example, I'm going to press function F4 to lock this value in place. And then I'm going to move down. What I can do now is switch what I displayed. So under design, you can select your data again. I'm going to edit what I selected for this data set and move the selection one over. The color unfortunately changed again. So the fill should be solid and in a blue color to be a better match for the Bradford signal. You could do the same with the data at 480, because clearly in all these washes and in the buffer, there was hardly any PPO left. So 480 minus baseline. Yeah, I'm going to subtract all the values for one of the buffers. And to select the data, I'm going to edit this data series. I'm going to move to the baseline corrected signal. Fortunately, again, I have to change the color. So the solid fill for this shall be orange or dark orange, more aligned with how the PPO activity assay looked like. My plot area should probably get a solid borderline to stand out a bit more, not in orange, but just in black. I shall not just have numbers that the reader needs to interpret, but for the axes options, the way I want the numbers aligned would be, or the labels, the text direction shall be rotated by 90 degrees. And I would like a real y-axis, so only for the vertical axis. This would be the optical density recorded at 480 nanometer or 595 nanometer. And this would be one possible way to showcase the data of this experiment. we can see that the starting material was very rich in PPO activity. The protein content signal is surprisingly low in this example, especially if you consider that later MS1 and MS2 seem to have very high Bradford signals. So we can't really take these values as the absolute truth, right? We can just document the result in this graphical compact format and discuss some tendencies. We can also see from this presentation that after you injected the starting material into the column, the flow-through still had a lot of polyphenol oxidase activity and some protein escaped as well. The same is true for wash 1, but as you continue to inject more buffer A without any salt, that was the 20 millimolar tris pH 8, no more protein and no more PPO activity was able to elute from the column. As you switch to that medium salt buffer, however, with the help of the sodium plus and the chloride minus ions, the ionic interactions between the column material with the positive quaternary amine and the negatively charged amino acid residues on the surface of proteins were disturbed, so that with medium salt concentration, you were able to elute protein, that is based on the signal at 595 nanometer, and you were able to elute PPO, that is based on the signal at 480 nanometer for your PPO activity assay with dopamine as a substrate. Most of the PPO activity in this example was present in MS1, but it was also a good idea to collect MS2, MS3, HS1, and for this particular example, even HS2, the more high salt fraction still had PPO activity.